Hello, welcome to Basics of Noise and its Measurement. This is week 5 of this particular course, and today specifically we are on the third day of fifth week of this course. And what we are going to discuss today will be introduction to Fourier integrals and why do we need these entities. So we'll discuss Fourier integrals, but before we discuss that, I just wanted to give you a backdrop as to why is it needed. So we have discussed that the approach of using Fourier series expansions of any functions, they work when the function is periodic. When it is periodic, it repeats itself after a finite duration of time. Now one question would be, what happens if this periodicity or the duration of this periodicity, it becomes very large and actually it becomes infinite? Then what happens? So that is what we will do in today's class, and then in the next class we will actually explore Fourier integrals. And what we will do is we will extend the method of Fourier series in context that what is happening as t becomes extremely large, and we will do that using an example. So I will consider a function ft, and it is such that it can have three values, 0, 1 and 0. It is 0 in the limit when at times when t is more than the time, half of the time period, and it is less than -1. The value is 1 when t is between 1 and -1, and the value is t over is 0 when the time is anywhere between t over 2 to 1. So first let's plot this thing. So this is my x-axis, this is f of t, and the value is 1 between -1 and 1. This is my time axis, and then the value becomes 0, and let's say this is the time period. So this whole thing is t over 2, and this thing is also t over 2. So this is t over 2, this is minus t over 2. Okay, and the function repeats. So if it has to repeat, then again after it becomes positive. Oops. So it repeats after a time period of t, and we will assume here in this context that t is more than 2, at least it's more than 2. So what we will do is that we will compute the values of a0, an and bn for this function. It's a fairly straightforward process, and then we will make certain observations that what happens to these values of an, bn and a0 as t increases, and how close they become to each other. So that's what we are going to look at. So a0 is equal to 1 over t minus t over 2 to t over 2 ft dt, and that equals 1 over t. ft is 0 at all locations in over the time period except between -1 and 1, and the value is 1 in this range, so it is 1 times dt, okay, so equals 2 over t. Then an equals 2 over t minus t over 2 to t over 2 ft cosine of nt dt. Oh, I'm sorry, this should be 2 pi n t over t dt, and as I explained earlier, because the value is 0 at other positions, so all I have to do is I have to integrate this only in the limits of minus 1 to plus 1, and the value of ft in this in these limits is 1. So what I get is 2 over t integral of minus 1 to 1 cosine 2 pi n over t dt, which equals 2 over t sine 2 pi n t over t into 2 pi n in the limits minus 1 to 1, okay. And I can also simplify this as I can remove this and I can make it 0, but what I have to do here is I have to multiply this by another factor of 2, so this becomes 4. So when I do all this math, essentially what I get is 2 over n pi, what this should have been is t into this, so tt cancels out, so it's 2 over n pi times sine 2 n pi over t, okay. So first thing is that a0 is 2 over t, so we will write down the results. A0 is equal to 2 over t, an equals 2 over n pi times sine 2 n pi over t, and if you do the math, bn actually comes to be 0. We will not go into that, but please do it, make sure that it comes out as 0. So now what we are going to do is we are going to make some observations, and we will look at the amplitude spectrum of this function. So our original function is equal to 0, 1, 0 for the limits minus t over 2 to minus 1, minus 1 to 1, and 1 to t over 2. I will do one more thing. So what I will do is I will make a table. And we will look at different cases of values of t, different cases for values, different, we will look at these constants, how they change and how closely or far they become from each other as t changes. So the first case we will look at is that t equals 4 pi. Why did I choose this 4 pi? Because if I put 4 pi in the denominator, this pi goes away, so my mathematics becomes easy. That's the only reason. But all what I am going to do is I am going to increase t. So first case is, this is case 1, t is equal to 4 pi. Case 2, t equals 8 pi. So I am going to double my t. Case 3, t equals 16 pi. Okay. The second thing I am going to look at is this parameter. Okay. So I will call n pi over t as omega n, some number omega n. Okay. So in this whole thing, t can vary and n can vary. Okay. So in the vertical direction I am varying t, and in the horizontal direction I will vary n. So n is equal to 1, n is equal to 2, n is equal to 3, and here we will look at omega n first, and in this case, and then we will also look at this sign of omega, this sign term. Actually, we will not worry too much about the sign term, but it's the omega n which is important. Okay. Similarly, here also we will look at omega n and sine, and then omega n and sine. So just to differentiate, this is n equals 1, this is n equals 2, and this is n equals 3. Okay. So when t equals 4 pi, time period is 4 pi, and n equals 1, I can calculate n pi over t, and what I get is that I get this value as 0.25. N pi over t is 0.25. When n is equal to 2 and t is equal to 4 pi, I get this value as 0.50. And when n is equal to 3 and t is equal to 4 pi, I get this as 7.5. Okay. Next, let's look at this 8 pi row. So when t equals 8 pi and n equals 1, then this omega n becomes 0.125. Here it becomes 0.25. And here it becomes 0.375. Okay. And then when it is 16 pi, t is 16 pi, then it becomes 0.0625. And in the column corresponding to n is equal to 2, it becomes 0.125. And here it becomes 0.1875. So let's look at this table more carefully. And then now that I know omega n, I can also calculate the sign values of things in the bracket. But so you can fill up this column, these columns. But the point what I am trying to make is somewhat different. That what this tells me is that when time period is 4 pi, on the time axis, the first Fourier component corresponds to omega n is equal to 0.25. The second Fourier component corresponds to omega n is equal to 0.50. And the third Fourier component corresponds to omega n equals 0.75. So we get successive Fourier components, and each Fourier component is separated by a spacing of 0.25 radians, right? When t is equal to 8 pi, time period has doubled, then this spacing goes down. In this case, the spacing was 0.25. In this case, the spacing was I will not write it here. But anyway, in the first row, the spacing was 0.25. Successive points were coming every 0.25 radians. Now they will come at 0.125 radians. So as I doubled my time period, the spacing between individual Fourier components of which represent the original function, this function, they are now closer. Which means that the Fourier components have become more dense on the x-axis, on the time axis. This is important to understand. When I increase my time period to 16 pi, I have increased it by another factor of 2. Then omega n, first omega n is at 0.0625, second omega n is at 0.125. So again, the spacing has shrunk by another, by a factor of 2 one more time. Okay. So now the Fourier components which correspond to the original function f of t, they have shrunk, they are even closer on the x axis to each other. So what this shows is that as I keep on increasing the overall time period, I will have closer and closer Fourier components if I measure the distance between these two Fourier components on the x axis. Then the distance between them will be reduce progressively as t grows up, and when t becomes infinite theoretically, then the distance between two Fourier components will be theoretically 0, which means that they will be to represent a function which has an infinite time period. I will need how many frequencies? Infinite frequencies to represent them on the frequency spectrum. If I have to generate their spectrum, then I will need infinite frequencies to represent them. So that is what this exercise shows us, that if I use this Fourier analysis approach and I make t theoretically infinite, I will need infinite number of frequencies to handle such a function. So if I have a function which has a finite time period and it repeats after finite time period, then I have a finite number of frequencies. The higher the time period, the more closely spaced are the frequencies. The number of frequencies is anyway extremely large, and goes from 1 to infinity. But when the time period becomes infinite, the distance or the separation between two adjacent frequencies shrinks to 0. That is what the point is. So this is a very important takeaway, and the context of this is that in a lot of situations our signals which we want to analyze, they are not periodic. For instance, I am talking to you, so I do not talk the same thing every 5 seconds or 10 seconds. This is not a periodic signal, and if I want to do a Fourier analysis of this, then I will need a very large number of frequencies, and two adjacent frequencies will be separated by almost 0 distance to represent them, and that is the context. And in that context we will introduce the next topic, and that is called Fourier integral. So that is what we are going to discuss in the next lecture, and thank you very much, and we will see you tomorrow. Thanks.